All right, so today, one of my favorite subjects, large deformations. We'll talk about the high-level aspects of when you need to consider large deformations and all those good things. And then hopefully, if we have time, we'll dive into a little bit of the background, the theory that underpins how exactly we accommodate finite deformations in the finite element method that we've constructed up to this point. Okay, so like I said, we're going to talk about geometric nonlinearity. What the heck is it? How exactly do we quantify large deformations? And what do we exactly mean by large? How large is, large enough to be considered within this kind of large deformation framework? We'll talk about when you need to consider large deformations in an analysis setting and for engineering design purposes. And then finally, we'll dive into some of the gory details. So just to refresh your memory, we talked initially on this subject of nonlinear behavior in finite element analysis as encompassing potentially two different types of nonlinearity: geometric nonlinearity and material nonlinearity. And we dwelled quite a long time on this subject of nonlinear material behavior because I think it's probably one of the more common phenomena that you might try to model. We talked about a whole bunch of different types of material nonlinearity. And effectively, at its core, material nonlinearity is really just representable as some nonlinear relationship between stress and strain in some chunk of material. That could be plasticity, could be damage, could be a bunch of different things. But really, it's just confined to the material. So outside of that, the other type of nonlinearity that we might encounter is something called geometric nonlinearity, which, to put it rather simplistically, is kind of like saying that not just is there a nonlinear relationship between stress and strain, geometric nonlinearity is characteristic of a nonlinear relationship between strain and displacement. And you might think, well, how can that be? That seems unusual. Well, how exactly do we get nonlinear behavior in our relationship between strain and displacement? And it's certainly not clear from this diagram that I've shown here in this one-dimensional case where I have a spring, I'm stretching it in one dimension, and how exactly can this exhibit any kind of nonlinear relationship between strain and displacement? In the way that we've chosen to define strain, how exactly does a nonlinear relationship arise? Well, we'll have to dive into some of those details as we go along, but suffice it to say, things become more complicated if, let's say, this spring didn't only deform, let's say, along some one-dimensional axis, but if instead this spring were allowed to rotate, possibly, and rotate not just by a little bit, but potentially by a large amount. That's when you might have to worry about, well, does the actual orientation of the spring matter for determining what its internal state of strain is and how that internal state of strain depends on the amount of displacement occurring at the end of the spring? So a good example of this in practice is kind of an analog to exactly that statement. Consider not a spring, but a beam, or if you like, some kind of beam column. So I have some beam shown on the left with its initial undeformed geometry and with some applied loads at the end of it. So I have some axial load P, I have some transverse load W acting downward, and I'm not showing the vertical shear force or the axial reactions at the support. Suffice it to say that can be relatively easily determined. Certainly the vertical shear force should be W, the axial reaction force should be P, acting equal and opposite to the end loads. What I want to call your attention to is this reaction moment at the end of this beam. Now, if you were to look at this problem and say, I know how to solve this problem, I can just use statics, right? Classic statics. I don't have to do anything fancy. Okay, we can do that. All we have to do to determine what is this reaction moment is do a sum of forces, or more specifically, do a sum of moments. So pose moment equilibrium of this structure with these applied loads, and we can figure out that this applied moment has to be directly proportional to the transverse load multiplied by the overall length of this beam. Okay, makes sense, right? That agrees with our intuition and our kind of classical reasoning from statics and all that. But now, what if I said, well, maybe this beam was either really, really long, or maybe it was relatively flexible to the extent that when I put these loads on this beam, it happens to deflect quite a lot, a non-negligible amount, which I'll call capital delta. So under this kind of transverse loading and under that transverse deflection, now suppose we came back, we went into the laboratory, we ran this experiment and we kind of constructed this beam, we put the loads on it, and then we could actually measure what that deflection is. Now I asked you, what's this reaction moment? Knowing now what the deformed state of the structure looks like. Now the analysis, theoretically you could proceed in the same way by supposing that I can, use simple statics, pose equilibrium of this structure, but I would have to take into account that the location of the applied loads, especially the axial load P, is going to be shifted downward by this amount delta. At least if I'm being honest about how the structure is behaving and how it's deforming. And under those conditions, if I were to say, do the same process, pose moment equilibrium, and then figure out exactly what is this reaction moment, I would notice that it actually differs from that kind of sum of moments equation that I got if I posed equilibrium, assuming that the structure was perfectly rigid and stayed initially and totally straight. If it deforms even, a little bit, this delta actually starts to contribute some amount of moment that's proportional to this moment arm delta multiplied by the axial load P. And in general, this kind of effect is sometimes referred to as the P delta effect. It's the effect that arises because you might have some small kind of imperfection in a beam or something that causes some kind of transverse deflection to occur, and the axial load internal to this beam column actually induces some additional internal moment or internal forces that are proportional to the amount by which it's deflected transversely. And it turns out that this is effectively a nonlinear geometric effect. And as the amount of deflection increases, it no longer becomes reasonable to kind of have done our analysis of statics considering only the undeformed geometry alone. So effectively, a succinct way to describe geometric nonlinearity is to be true to the reality of this scenario and to always choose to pose our equilibrium equations not with respect to the undeformed configuration of some structure, but to instead pose equilibrium with respect to the actual deformed geometry of the structure. So if you're trying to reconcile all these concepts, this is probably the simplest example and the simplest definition I can give you. So geometric nonlinearity is all about posing equilibrium with respect to some deformed configuration. But that might sound a little bit strange when I just said that geometric nonlinearity can be characterized just by coming up with some nonlinear relationship between displacement and strain. How does that become reconciled with this scenario? Well, you'll have to see and kind of just trust me that there's a way to demonstrate exactly how that comes about by introducing a nonlinear relationship between displacement and internal strain in the structure. It turns out that you can capture exactly these types of effects. So kind of an interesting thing, but we'll get there. We'll get there. Okay. Now, another good question is, well, how big do the deformations need to be for me to be worried about them, for me to have to actually consider them in the analysis? In other words, when is it okay to just do simple statics and assume that the structure remains perfectly rigid and that the actual deformed state of the structure is irrelevant for the sake of engineering design calculations? Well, unfortunately, it would be nice to say that there is a particular amount of internal strain in the material or the amount of total deflection of the structure at which you should definitely consider large deformation effects. Unfortunately, there is no such limit. And partly the issue has to do with kind of that P delta effect, especially when you're considering things like buckling analyses. Even just a small amount of transverse deflection of this beam, or maybe this kind of axial column subjected to purely axial loading, even just a small amount of transverse deflection under high axial loading can drive an instability. So a very, very large axial load with a very small delta can, result in a further increase in internal moment, which further drives, more transverse deflection, and it's this kind of reinforcing cycle. So that kind of phenomenon is likely what you're familiar with as buckling. It's the behavior of an instability that's driven primarily due to a geometric nonlinear effect. So buckling really, and buckling analysis, requires that we pose equilibrium with respect to the deformed configuration of some beam or column when subjected to axial loads. So anytime you're doing some kind of stability analysis or some kind of column buckling problem or any kind of buckling analysis, you need to include geometrically nonlinear effects. And if you're doing it by hand, certainly, there are kind of existing equations like the Euler buckling equations that take that into account. But if you're running a finite element analysis and you want to include buckling effects, then you need to include large deformation features. So turn on that kind of toggle button within your finite element code if you want to get that to come about. But again, I want to reinforce the point that even just a small amount of deformation can lead to a larger instability. It's kind of like saying that, maybe this column, if it remained perfectly straight, it would be in a state of equilibrium, but that state of equilibrium would be unstable. It's kind of like saying, try to take some ball rested on the top of a hill. It's certainly going to remain in equilibrium if it stays perfectly on the top of this hill, but, nothing's to say that maybe a small gust of wind could blow it one way or another. It's an unstable equilibrium. So in these kinds of situations, you do really need to take into account even very small deformations. So that's kind of an unfortunate reality you have to deal with. Okay, now, when apart from buckling analysis, when do we actually need to consider large deformations? Well, it spans a whole bunch of different scenarios in which you might want to try to include these features, turn them on. Certainly, buckling analysis is one. If you're trying to assess, when will this single member fail or in buckling? Or when will the whole structure fail under some kind of unstable mode of deformation? Those are things that you need to include. Other scenarios where you do need to include large deformation effects are when you're dealing with materials that are inherently flexible or deformable. And typical structural materials in general are not particularly deformable. When you think about steel, concrete, or other types of materials like that, they don't really deform very visibly under any applied loads. But there are other materials that certainly these common structural materials come into contact with that do exhibit relatively large deformations. Things like rubbers or other types of elastomers. Soil is probably another good example. Foams, a bunch of other types of materials like that that are relatively flexible and undergo large deformations. So for those types of materials and analyses that include them, usually it's a good idea to turn on your large deformation effects. Also because they happen to exhibit somewhat nonlinear elastic behavior, and to include that kind of nonlinear elastic behavior, it's also useful to actually treat it as a form of geometric nonlinearity. It's kind of weird. Other types of scenarios in which you might have the need to include large deformations are things like if you have any kind of piece of machinery, either the structure itself is flexible or can kind of freely rotate or kind of like move about, like it's some kind of machine or mechanism, as you might have, let's say, with a wind turbine, where the turbine is spinning. Even though, let's say, the strain in the individual blades of this turbine, maybe the strain in those blades is not particularly large, but if even just the rotation of some object becomes large, that still qualifies as large deformations and requires that you include these kinds of large deformation effects. Other scenarios are anytime you're dealing with material nonlinearity, and especially if that material nonlinearity leads to some kind of collapse mechanism or failure mechanism, to be able to adequately represent that failure, not only do you need to have material nonlinearity, you probably should also be including geometric nonlinearity, in part because that kind of loss of stiffness of the structure leads to kind of a relevant increase in the apparent stiffness of the structure, and then you get into this kind of territory, where it's kind of like as the material resists or it fails to resist some applied load, it might deflect significantly. You might start to get that P delta effect in some of these columns. And to be able to resolve what's going on, you might need to actually turn on large deformation. And then the other one that we talked about last time, if you have elastoplastic necking types of problems or strain localization in some kind of chunk of material, to actually represent that and to represent the fact that really the stress across this deformed cross-section of this necked specimen, because it's becoming smaller, technically speaking, the stress across that cross-section should take into account the fact that the cross-section has decreased. So that is effectively a geometrically nonlinear effect. Changes in the actual deformed shape of the structure do influence how the loads get transferred through those structures and can lead to phenomena like strain, heart localization, and necking. So those are situations where you might need to include it as well. So that's all geometric nonlinearity and when you need to include it. But the good question that you would follow up and ask, knowing all these things is, well, how exactly do we include that in our analysis? I said before, if you wanted to do these kinds of analyses, all you really need to do is go into whatever drop-down menu, turn on, large deformations, and you're done. You don't have to really fuss about like how exactly, these considerations of large deformations, how do they influence the actual finite element computations? But of course, I'm going to give you the background. We could end it here and say that's geometric nonlinearity. Go have fun. Play around with it. You certainly do play around with it, but I do want to give you a little bit more insight and kind of explain, especially how exactly this, supposition that a nonlinear relationship between strain and displacement somehow gives us all of these interesting behaviors that I previously described. How exactly does that come about? And to really understand that, we have to kind of go through this process of actually establishing a particular nonlinear relationship between some new strain measure and the displacements that might occur in the structure. Once we have that, then we can actually go about deriving what's the new nonlinear relationship between displacement and internal force in the structure. How exactly would we come up with an expression for the stiffness matrix? But we can't do any of this. We can't do these subsequent steps of coming up with a nonlinear geometric finite element kind of method unless we start from number one, unless we come up with this new nonlinear relationship between strain and displacement. So how exactly do we do that? How do we come up with some new measure of strain, what I'll call finite strain? That is to say, strains that are not super, super small. Finite strain really means strain that could become possibly larger than zero, obviously, but sufficiently large that it starts to influence and change the apparent geometry of the structure. So you can imagine, maybe like a couple of fractions of a percent strain that you might see in some structure aren't really going to change the shape of the structure. And typical engineering materials really don't undergo significant strains in a lot of surface loading conditions. But if you have, strains that are approaching on the order of like, a couple percent to like 10% or more, that's kind of where you're in the danger zone, where you might want to think about, maybe I need to have like large deformations turned on in my analysis, because that could significantly change the overall, geometry of your structure. But if I'm trying to come up with some new measure of strain that introduces this nonlinear relationship between displacement and strain, there are a few conditions that I have to put on this new measure of strain. And the strain that we've been working with up to this point is the so-called small strain tensor. It is, as we had previously defined, this kind of symbol epsilon, which we had defined as basically the symmetric part of the displacement gradient. If you like, explicitly, something that looks like this, where I have my displacement gradient tensor, nabla u, which characterizes the gradient of these kind of like components of the displacement with respect to each of the coordinate directions x, y, and z. So that was kind of the small strain tensor. And I say, in formulating some new measure of strain, something other than this small strain tensor, I need to at least guarantee that if the deformations do happen to be small, then at the very least, I should come up with a similar description of strain that agrees in that limit with this small strain tensor. So if I have some alternative description of strain, it should nonetheless reduce to the small strain tensor in the limit of small deformations or small strains. And one other condition I have to impose on this new measure of strain is that whatever measure of strain that we develop, it should be insensitive to rotations. Strain should not include any kind of dependence on rotation. You can kind of imagine that by saying, imagine I had some kind of uniaxial bar. Imagine I attached a strain gauge to that kind of bar. If I chose to spin this bar in midair, that strain gauge is going to be measuring kind of the axial strain in this bar. And that strain gauge will be rotating along with this bar, right? So in some sense, what we want to come up with is a description of strain, like this strain gauge that we might attach to this kind of bar that's spinning. We want to come up with a description of strain that is kind of attached to the material and rotates along with it. So that's a little bit different from saying, take this bar, let it rotate, and then suppose that we measure the strain by still assuming that the strain gauge was always kind of maintaining its same original orientation, regardless of how the bar was spinning. If you let that happen, then it's kind of like you're introducing some dependence of that strain on the amount of rotation that the bar has undergone. But that's not really physical. And strain never really measures rotation anyways. It's always just a description of how much stretching is happening in the material, but it doesn't care at all about how much the material might have rotated. So that's the other condition. We need to have it be consistent with this small strain tensor, and we need to make sure that it doesn't depend at all on how the material might be rotating. Okay, so those are the conditions that we seek in coming up with some new measure of strain. And before we even get to strain, we have to kind of backtrack a little bit and describe what we mean by deformation. So up to this point, we've talked about some, description of a structure. Let's say, a structure in its relatively undeformed state prior to any loading being put on the structure. And I've tried throughout the course to at least maintain some consistency with respect to the notation, where if I have a structure which is represented in its undeformed configuration, is how I'll refer to it. So before any loading has been put on the structure, the coordinates of specific points within this structure, I will denote their coordinates with capital X. So that will denote some kind of initial position of some point within the structure before I've put any loading on it. But once I put loading on the structure, this particular point within the structure might deform. It might, translate into some new coordinates, and it will displace by some amount u, some vector that describes the motion of that specific material point x. And its new deformed coordinates, which I'll denote with this lowercase x, within the deformed configuration of this structure, again, can be interpreted as just the original coordinates, capital X, plus the amount by which that coordinate has displaced u. So if you like, you can treat these coordinates, lowercase x, as really just the summation of capital X plus u to give me the new deformed coordinates of some point in some structure. But we have to distinguish now between two different configurations of the structure. Just as we did when we were looking at that P delta example, we have to distinguish between the undeformed configuration of the structure, the initial conditions before we put the loads on, and this final configuration after the structure has deformed. So I'll try to distinguish between those things where anything that's defined relative to this initial configuration, I'll use capital letters in this kind of darker gray color. And if I'm talking about the deformed configuration of the structure, I'll try to use lowercase letters and this sort of darker blue color. Okay, do let me know if you have issues with the color scheme or if it's a little bit hard to distinguish. Okay, so now that we've kind of reconciled that we have to actually introduce a description of a structure that takes into account both its undeformed and its deformed configurations, now we can kind of start to talk about how exactly that fits into the context of a finite element analysis and how we can start coming up with strain measures. So remember, way back, this is kind of a nice review subject because we get to jump back to some of the old topics that we talked about a long time ago. Remember when we were talking about finite elements, really, we had to distinguish that each one of these elements could be described as some collection of nodes, and actual positions internal to each one of these elements we interpolated using our kind of classical isoparametric transformation. So any internal point within this element in its undeformed configuration can be identified as some kind of distinct point, which I'll call capital X. And if I wanted to note how much does this particular point displace internal to this element, well, I can figure that out by supposing that each one of the nodes of this element will also displace after I run an analysis. And this is sort of the paradoxical thing about running an analysis that is inherently nonlinear. We want to know what is the deformed state of this structure so that we can kind of figure out what are the loads that act on it, but we don't really know exactly how much it's going to displace by. The displacements of the structure are the primary unknowns that we're solving for, but we need to know those displacements in order to figure out what this deformed configuration of the structure is. So back to the subject of nonlinear analysis being an inherently iterative process. And we kind of have to make an initial guess of what we think the displacements of the structure are, so that then we can say, okay, given this guess for what we think the displacements are, now we have some guess for what we think the deformed state of the structure is going to look like. And from that, we can come up with descriptions of what's then the strain in this assumed deformed configuration of the structure. We can determine what are the resulting internal forces that would result from that deformation. And then we can kind of go through that whole process, verify, does it actually satisfy equilibrium? And if it doesn't, then we have to go back and make an updated guess for those displacements. But supposing that we've done that process, we've iterated, we've kind of come to an equilibrium converged state, and we know now what the deformed kind of displacements of each one of the nodes are. Now we can come and say, well, each one of these nodes who might have had original coordinates capital X, each one of these nodes will displace by an amount that's proportional to capital X plus the displacement of that corresponding node, U. And we can represent now the element with respect to its undeformed or its deformed configuration. So what that means is individual points internal to this element can be mapped directly to points that exist in the deformed configuration of this same element. And we could do that directly by supposing that there is some functional dependence of the position of these interior points, lowercase x, which depends in some sense on the original coordinates of these points. But that is somewhat difficult to construct. And in practice, we don't actually do that. Instead, what we do is we refer back to some reference coordinate frame that directly corresponds to the element's parametric domain. So remember, way back when we were talking about isoparametric transformations, every element has some associated parametric domain that is a nice perfect square. And usually it has bi-unit dimensions. So a length of 2 on each one of these different sides. Now, within this parametric domain, we can identify specific points in terms of their parametric coordinates, that psi variable. And we can relate that psi variable through our isoparametric mapping to some corresponding point that lies inside of the element. In the case of large deformations, now there are actually two configurations that we can choose to map these parametric points to, either points within the actual undeformed configuration of the structure or points within the deformed configuration of the structure. In either case, the only thing we have to change is which nodal coordinates do we plug into these expressions for the isoparametric transformation. If we're looking at the undeformed configuration, then we have to use the undeformed nodal coordinates or the initial coordinates before any kind of loading has been applied. If we're looking at the deformed configuration, we have to use the deformed nodal coordinates, the lowercase x. So subtle distinction, but effectively what it means is that we have two isoparametric mappings, one for each of these two configurations. And in addition to having isoparametric mappings, one for each of these two configurations, we also have Jacobians. Remember the Jacobian. The Jacobian was really nothing more than the partial derivative of that kind of isoparametric transformation that was, in some sense, the partial derivative of this coordinate x with respect to the parametric coordinates. And you went through several exercises in the homework to kind of reconcile and hopefully get a better intuition behind what exactly this Jacobian represents. But again, here too, there are two Jacobians, one associated with the undeformed configuration and one associated with the deformed configuration. I'll remind you of the geometric interpretation of what this Jacobian is actually doing. The Jacobian, in some sense, provides a direct relationship between differential line segments or scratches defined in the element's parametric coordinate domain. And it takes these independent line segments and transforms them into some deformed collection of line segments in the element's actual, physical coordinate space. So some small differential line segment, dc here, originally perfectly aligned with the c direction, would be transformed through this Jacobian mapping into this kind of vector that has direction that's directly proportional to dx dc, and with kind of corresponding length dc tacked onto it as well. Now, if you happen to look at the deformed configuration of the structure, now this same line segment dc would actually be mapped somewhat differently into a different vector with different orientation based on the Jacobian associated with the isoparametric transformation for the deformed configuration. So the same line segment originally in this parametric domain looks different depending on, whether we're looking at it in the undeformed configuration of the element or in the deformed configuration of the element. So the nice thing about this kind of notion of looking at how the Jacobian transforms these line segments is that it kind of gives us a way of tracking how do these individual line segments deform, and not just how much do they deform, how much do they stretch out. And that will be helpful as we try to develop these measures of finite strain. So it turns out the Jacobian is a particularly nice starting point for measuring stretching and deformation associated with small kind of line segments as you might need for measuring strain. Now, the last thing we need to do in putting this all together is to not just suppose that there's this weird fictitious parametric domain. It has no physical interpretation in the context of reality. It doesn't make sense to always be referring back to this parametric domain to figure out how these line segments are stretching. So instead, what's commonly done is to come up with a direct relationship between how line segments in this element's initial undeformed configuration deform if you happen to go through this whole sequence of operations. So suppose I had some kind of initial line segment, dx, which was originally perfectly aligned with the x coordinate direction. And also kind of imagine like I'm attaching a strain gauge to this small line segment. So what I really want to find out is how much does that line segment stretch out? And maybe it will rotate a little bit, but I don't care about the rotation. I just really want to know how much is it stretching. So in order to figure out how much it's going to stretch, I have to figure out how it looks like in its initial undeformed configuration and what it looks like in this deformed configuration. And to get there, I actually have to traverse through my parametric coordinate domain. I have to actually use the inverse of the Jacobian to take this line segment and map it into a corresponding line segment defined in the element's parametric domain, and then use the Jacobian associated with the deformed configuration to take that line segment and deform it again into the element's final deformed configuration. So a total of two mappings. First, the inverse Jacobian, then this kind of forward Jacobian. And if I put those two mappings together, if I kind of take each of these two matrices, the inverse Jacobian and this kind of forward current Jacobian, multiply them together, what I get is a new mapping that happens to be just kind of this representation, which can be represented as the partial derivative of the final deformed coordinates of the structure taken with respect to the initial undeformed coordinates of the structure. And this mapping is sometimes referred to as the deformation gradient. It is, in short, a description of how individual line segments are deformed after deformation. So this small dx will get mapped into this corresponding dxdy, or yes, this might be a block. Anyway, those two need to be flipped back, but hopefully you get the idea. The idea is each one of these line segments will be rotated and potentially stretched a little bit. And that relationship between how those line segments get deformed is maybe a little bit more clear on the next slide. If I had some initial line segment dx1, the relationship to this corresponding line segment, the lowercase x1, is established through precisely this relationship involving this deformation gradient quantity. So it's a matrix. I multiply it by this kind of differential line segment represented as a vector, and I get a new vector that is potentially rotated and also potentially scaled. And it's worth noting that this deformation gradient will operate on different vectors in different ways. So this dx1 will be rotated and stretched, whereas this dx2 will be also rotated, but it'll be not stretched, but actually shrunk a little bit. So depending on the initial orientation of the line segments that you're looking at, the line segment might stretch or rotate in slightly different ways. So unfortunately, that's as much as we're going to be able to get through in today's lecture, but we'll pick up on some of these subjects on Friday. Okay, until then.